Well, hi everyone, we'll be starting in about 1 minute time. Alright, good afternoon everyone. Now, I know the title of the video says Lecture 16 Fourier Series 1, but it's supposed to be Lecture 16 Fourier Series 2. So, today's lecture is going to focus on how do we use the Fourier series in particular in its trigonometric form, and how do we solve for those Fourier coefficients that we saw in the trigonometric form with respect to yesterday's lecture. So before we actually get to that, I want to explain what are even and odd functions, because this actually helps us speed up the process when we're trying to solve for those Fourier coefficients in particular. And reason being is that later on you'll see that the AK and BK coefficients in the trigonometric form of the Fourier series actually represent even and odd components in particular. And once we can prove that a function is even or odd, that means that one of those components, AK or BK, will just automatically equal to 0, meaning that you don't need to do the long integration in order to resolve it as of such. So we're going to be starting off with describing what are even and odd functions, and then we'll see the importance of why even and odd functions are for the Fourier series in particular, and I'll explain that later on when we actually hit one of the in-class examples. So for any arbitrary function here, f of x, we can basically say f of x is even if we basically reverse the signal altogether and we obtain the same signal. So that just means that f of x is equal to f of minus x. So once we have the same signal that can be represented when we basically flip the signal horizontally, we basically say that this function here is even in nature. And as of such, that means they have symmetry about the y-axis. So if we reflect this part here onto the left-hand side of the y-axis, and the left-hand side here to the right-hand side, by doing this as f of minus x, we basically see that we get back the same f of x function here. So once we can do this, we prove that the function is even altogether, and this will work for any continuous time arbitrary function f of x. For an odd function, on the other hand, we have to reverse it first, and then we invert it vertically. So we reverse it, meaning that we flip it horizontally, and then we invert it, meaning that we then flip it vertically. So basically, let's take this f of x function here for odd, and to give you an idea how we do this, basically let's say that we flip this horizontally, so we go f of minus x, and what that will look like is that we'll have this right hand side here will be something like that, and then the left hand side here will go something like this. And then if we invert it, meaning that we flip it vertically, what we end up is that we get this here, and this here, which basically is the same as our f of x function. So once we could maintain this relationship here, such that we flip it horizontally and then we flip the result here vertically and get back the same f of x function, we basically say that this function is odd in nature. And odd functions basically have symmetry about the origin, meaning that they have symmetry about the 0 points for x and y altogether. But the better way to remember it is flip it horizontally first and then flip it vertically, and if you get back the same signal that you started with, the signal is basically odd. Oh, wait, one more thing. There will be some cases where even if you try to prove if a signal is even or odd, you won't get back the original f of x signal. So in those cases, the signal is neither even or odd for those cases. So if you sum odd powers of x, the resultant would be an odd signal regardless. And if you sum even powers of x, the resultant will be an even signal regardless altogether. And with respect to our Fourier series, basically that we saw there's a sine and cosine component with respect to our Fourier components. The sine x signal here is odd in nature, because if we flip this horizontally and then flip it back vertically, we'll get back sine of x here. And our cosine of x function is even, because basically if we reverse this signal altogether horizontally, we get back the same cosine of x signal here accordingly. So just remember this in particular, that sine signals are odd and cosine signals are even in particular. Because this is going to play a very important part when we actually hit the Fourier series evaluation for its trigonometric representation. Yes, and also, uneven functions here for products just basically follow like these properties here. So if you multiply two odd functions, the resultant function will be even. If you multiply two even functions, you will end up getting a resultant even function as well. And if you multiply an even and an odd function, you will end up getting with an odd function in particular. Now, let's say we integrate an odd function over a symmetric domain, meaning that we be watching it across the origin point here in particular. So basically, we'll be watching it such that we need to get the area for this curve here with respect to the x-axis, and we also need the area here under this curve with respect to the x-axis as well. So the general integral will be such that if here was p and here was negative p altogether, we'll be integrating with respect to those limits for the f of x function with respect to dx. But what you'll find out here is that when you get the area for this part here and the area for this part here, this is a positive area and this is going to be a negative area. And the two areas, because they're going to be the same magnitude, they'll just cancel out each other altogether. So if you're integrating an odd function which is going to be symmetric about this 0 point here, the resultant integral will be 0 altogether, so long as you're integrating between fixed limit points here, which are basically going to be positive and negative of the same limit point. If you integrate an even function about the origin here, and both sides are evenly spaced by positive p and negative p here altogether, we basically say that in doing the integral here, we'll get one area here, but we'll also get another area here, and both areas here are positive. So in doing the integration here, it's just going to be 2 times the integration of 1/2 of the signal here. So we just need to find the area for just only this part here, and then to get the total area, we just multiply by 2 altogether. And this only holds true if you're integrating about the origin, and the left hand side and the right hand side are basically the same space apart from the origin. So when we deal with periodic functions, and this is basically the main reason why I use the Fourier series, because it's for periodic functions. It's such that we can represent a repetition of the signal for every t instances. So such that this capital T here will be our periodic time, and for each instance when the periodic time repeats, we also get back our original f of x signal for every value of x here, as of such. And the smallest value of t will be called the period of x in particular. And some general examples are like our trigonometric functions being sine x and cosine x, and the general period is 2 pi. And then if we say pi x here in the brackets, it's going to be periodic with period 2 altogether. And if we have L being a fixed number here, and we will have sine 2 pi x on L and cosine 2 pi x on L, the period here is modified such that it will just be a period of L altogether. So, keeping all that in mind, we're moving towards our general form of our Fourier series equation here. And we have our A0 component being our DC component, our A of n cosine n of x component here, which is basically going to be our even components for the entire f of x, and the bn sine n of x component here, which is going to represent our odd components for f of x altogether. Now, this equation that I'm presenting here, just watch the range in particular. This is between negative pi and positive pi, and whereas this will work for general trig equations and so forth, which have a period of 2 pi, this isn't applicable towards any other periodic equations in particular. So we're going to be watching how do we modify this general equation here to work with any periodic signal. So once we have a period other than 2 pi, meaning that we can evaluate this function for any period in particular, the variables in the Fourier series will basically change. So if we have a fixed period of 2L in particular, t here is going to be pi x on L. And if we put this into our f of x function here, which is basically, let's say we have a placeholder named g of t here, and we substitute t here into our brackets as such, make an x the subject of the formula to get this. We basically see that if x becomes the subject of the formula, this is going to be TL on pi, which we get here in our brackets altogether. And because we have our general Fourier series here, in transforming it to represent for a period other than 2 pi, in this case a period of 2L, our A0, AN, and BN components here take these forms for respect to our integrations. So A0 will be 1 and 2 pi in between the limits of pi and negative pi of g of t dt. And AN will also be 1 on pi here for the limits of positive pi and negative pi of gt cosine n of t. And the Bn will be basically the same as A of n, but instead of cosine, it's going to be sine n of t here in particular. And after we do our mathematical manipulation and so forth and whatnot, the equation that we'll be using for solving any of the Fourier series components is such that we'll have our A0 equation here being 1 on 2L integrating between L and negative L of f of x dx. An here is equal to 1 on L integrating between L and negative L of f of x cosine n pi x on L dx. And our b of n equation, representing our even coefficients, are going to be 1 on L integrating between L and minus L of f of x sine n pi x on L dx. Sorry, I said the wrong thing. The sine coefficients here are odd, the cosine coefficients here are even. Alright, so let's actually apply the Fourier series equations that we just now saw here, shaded in green and blue. To solve for our Fourier coefficients for this general square wave function here defined by this equation. And we're also given the periodic property here of f of x to know what it is in particular. So basically this f of x here is going to be 0 between negative pi and 0, and 1 between 0 and positive pi. So the first thing that we'll do is that we'll actually draw out our equation to actually see what it looks like physically. And basically between 0 and positive pi we have a value of 1, and in between 0 and negative pi we have a value of 0. And because we know that the signal repeats itself every 2 pi cycles, we just basically draw repetitions of the signal itself. And once we actually have our signal drawn out here, we can actually recall our A0 equation here to actually solve for it in particular. So we know A0 was 1 and 2 pi integrating between pi and negative pi here of f of x dx. And the reason for pi and negative pi here is because we saw here that our signal basically went from pi here to negative pi here, and the span here was basically over 2 pi. So we integrate with respect to this. And we basically see that if we split our signal here, because half of it is going to be 0 and the next half is going to be 1, the integral part for 0 is going to be 0 and negative pi from our graph, and the integral part for 1 will be in between pi and 0. And once we conduct our integration as of such, we basically see that after we do our maths, A0 here is basically going to equal to 1/2 in particular. In solving for our an and bn coefficients, if we actually do the math for a of n here, we're basically going to see that this is going to resolve to 0. If we do the math for b of n here, we're basically going to see that we will end up getting a sine of nx function here, being that it will be 0, such that when n is even here in particular, the entire equation will result in 0. But if n is odd, we'll end up getting 2 on n pi in particular for our result. So in order to verify this answer, and this is going to be part of your homework, you're going to actually have to conduct the integration here for a of n and b of n and see if you get a resultant equation. And in particular, you don't really need to represent b of n here, saying if n is even and n is odd. Once you get down to its simplest possible form, in particular, you can immediately see that once you put in any even value for n, the entire equation will resolve to 0. Or once you have any odd value for n, it's going to resolve to 2 on n pi in particular. So basically, your question, if you get one in exams, will basically end such that you solve for A0, A of n, and B of n accordingly. And if you're required to write up the Fourier series, basically you just write it out like if it's going to be an expansion theory problem. And because you see here for the sine of x coefficients, the values follow a similar pattern, you can summarize this into a summation series in particular, and you can get it shortcutted into this form. But typically, for this course, you won't be asked to get this kind of form of equation. You will just be asked to solve for only the Fourier series coefficients in particular, which will be A0, An, and B of n. So for general practice as well, try solving for the Fourier series of this triangular wave function defined by this f of x function here. And we're also given the periodic property here for f of x as well. So to start you off a little bit, so that way you can see what's going on. Because this is modulus of x, this means we know that if this is going to be f of x here, our line here would basically be x. But in this case, because it's modulus of x, that means anything that's negative is now going to be positive. So whereas our line went this way on our positive side, for the negative side, when we knew that the line was basically going down negative here, it's not going to be reflected. So that way we get a positive value here in particular. And we basically see that this is going to repeat in between -1 and +1 here. And the time span here between that is going to be 2. So t here is equal to 2, but L is going to be t on 2, because L represents half our periodic time. So L will be 1. And basically, once you have these values here, you basically can actually solve for the equation in particular. Just keep in mind, because this is a reflected function here, this means that the equation for this part is going to be minus x in particular. So because you now have the equations for f of x here and you know what the L value is, you can actually substitute in accordingly and you can actually perform the integrations to solve for a naught, a n, and b of n accordingly in particular. Alright, so this basically brings us to the end of our Fourier series lecture in particular. And I suppose because we're finishing a little bit early, I'll backtrack a little bit. And I'll actually do the integrations for this in-class problem, so that way you can actually see how we solve for a of n and b of n in particular. So let me bring this down. Let's keep my ink. So let's bring up my whiteboard here. There. Alright, so for that in-class problem here, our f of x function was basically equal to 1, and I'm backtracking here so that I can check back on my slides. 0, sorry, for negative pi to 0. I believe it was less than or equal to. And then 1 here for 0 less than x. Then back, right. Oh, I have less than or equal to. Then f of x plus 2x is equal to f of x. So x of s plus 2 pi. So the slides basically show us the working for a naught, so I'm not going to bother with the working here for that. We're going to be moving on towards our an equation in particular. So our an equation here from our slides is basically 1 on pi in between pi and negative pi of f of x cosine n of x. I can check that. Right, nice. So let's actually put in our integral form here for f of x. So this being here 1 on pi means that we'll be going between 0 and negative pi of 0 cosine n of x dx plus in between pi and 0 of because we just have 1 here, cosine n of x. And if we resolve this, so what it's actually supposed to be, it's just going to be 1 on pi between pi and 0 of cosine n of x dx. And this basically here is going to resolve to 1 on pi. The integral of cosine will basically give us the differential of sine will give us cosine. So if you integrate cosine, we get back sine. So this here is that. Then we have 1 on n because we're differentiating, we have to divide that. Sine of nx. Oh, sorry. This no longer is an integral. This is evaluated here between pi and 0. we basically see at this point, once we substitute pi here and 0 here, for any value of n that sine of x here is going to take, in particular, the sine of nx here will basically just go to 0 in particular. So let's just resolve this out. So let's get 1 of n pi into sine n of x between pi and 0. And basically we can see that if it's sine n pi, that's going to be 0 in particular for all value n. And then when we substitute in 0 here in particular as well, this is just going to be sine of 0, and that's going to be 0. So a of n here would just end up resolving to 0. And if we watch our b of n equation, this was 1 on pi, integrating between pi and negative pi of f of x. So a an equation with respect to cosine, our bx equation will be respect to sine. So it's sine nx x. And if we resolve this, it's going to be 1 on pi in between pi and 0 of sine nx dx. Go to 1 on pi. Integrating sine would be that way such that we'll get negative cosine, because if we differentiate cosine, we get negative sine. So this is going to be minus 1 on n into cosine n of x in between pi and 0 here. So e of n will be minus 1 n pi in between cosine n of x between pi and 0. And let's resolve this out a little bit more so that we can see what it's going to be. So e of n being 1 on n pi here, negative. This is going to be cosine of n pi minus sine of 0. And cosine of 0 here just basically resolves to 1. So e of n here is what end up being minus 1 on n pi of cosine n pi minus. And if we flip this around such that we we change the signs accordingly, sorry, this will become 1 on n pi into 1 minus cosine n pi. So we basically saw here, and I'm backtracking to our slides, that b of n would be 0 if n was even, and then 2 on n pi if n is odd. So let's actually evaluate this to see how this resolves. So let's say that n here equal to 0, because 0 basically will be treated as even. So b of n here would be equal to 1 on n pi into 1 minus cosine of 0. I'm just checking this back to make sure my math was correct. Right, yep, my math is correct. And cosine of 0 here will just basically be 1, so we get 1 minus 1 here, so this will resolve into 0. But if we let n here equal to 1, e of n here will be 1 of n pi into 1 minus cosine of this here being just cosine of pi. And cosine of pi will basically give us a value of -1. So that there will be -1. And as such, we get 2 on n pi accordingly. So it actually proves our answer here with respect to our example problem here. So for any even value of n, it will resolve into 0. But for any odd value of n, we'll get 2 on n pi in particular. But when you actually doing your equation, once you reach to this line here in particular, you basically can stop working because this basically is going to be correct at that point, and you don't need to continue any further when you're solving for your Fourier coefficient. Right. So in attempting this particular problem, just make sure that when you're using the Fourier series equations here in particular, you want to be using these forms for a0, an, and b of n here. And the working that I did basically showed you guys such that we had the f of x equal to modulus of x here, so we got the two equations. And basically, we obtain our periodic time here being x plus 2 for f of x. And L here is going to be half our periodic time, so we obtain the value for L, and then as such, you can apply it to those Fourier series coefficients. So why don't we submit n equal to 1 on divided by n pi? Well, no, because in particular, when I was doing the evaluations here, I was just showing you for the brackets. So basically, and doing evaluation for brackets, even if I let n equals 0 here on the denominator, it just basically would make sense. If I said here n was equal to 2, this would be 1 on 2 pi here, and then we'll get 1 minus cos 2 pi, and cos of 2 pi would basically be the same as cos of 0, so this would end up resolving into 0 as such. So the only reason why I let n here equal to arbitrary values being 0 and 1 was actually just to resolve the values here in the brackets in particular. But this is similar to saying, okay, let n equal to 2, we'll get the same 0 value here. And if I let n equal to 3, we basically get the same 2 on n pi value here in particular. I'm just ignoring the 1 on n pi here in particular because I just want to resolve the values here in the brackets. Cosine of n pi in particular will end up being such that it's -1 to the power of n plus 1. I believe so, because let's see, we're going to be dealing with odd values here. So if we go cosine of pi, let me get a calculator just to show. Let's say cosine of pi will be -1, then cosine of 3 by pi. No, it's still going to be -1 regardless. So it's not going to be -1 to the power of n plus 1. Because cosine pi and cosine of 3 pi will give us -1, and if we solve for cosine of 5 pi, we'll get -1 regardless, because we're just dealing with odd powers of n for b of n. Sorry, not odd powers of n, we're dealing with odd values here for n to resolve this value here in particular. Right, so just to recap a little bit, I basically drew out the f of x function here for you guys to do for homework. So you have the f of x function here being modulus of x, and in drawing this, we basically saw that instead of having the negative line here, we'll have the positive line here. And this will basically go to negative x and positive x in particular. So because we have the equations here being represented between -1 and +1, we have our f of x equations, and we have our periodic property here, which was f of x plus 2 equal to f of x. So t here is basically equal to 2, and L being half of t means that L will equal to 1. And because we have our L here and our f of x equations here, we can then apply it accordingly to our Fourier series equations here with respect for period 2L. Yes, b of n will be equal to infinity when n is equal to 0, but just for ease of mind, because I understand what you guys are saying here, if we let n equal 2 here, and resolve the brackets here, this will just end up being cosine of 2 pi, and cosine of 2 pi basically just give us 0. Sorry, cosine of 2 pi will give us a value of 1, and the value in the brackets would resolve. Let me just draw it out for you guys. This here will resolve to a value of 1. And 1 minus 1 here in the brackets will just end up being 0. But like I said, when I was substituting the values for n here in particular, oops, trying the wrong thing. Right. When I substituted the values for n here in particular, being n equals 2 and n equal to 1, I'm just resolving the value here in the brackets. I'm not taking into consideration this 1 on n pi here in particular. Because for any of these values here, being when n is even, this entire thing here will just resolve to 0 altogether. And then when n is equal to 1, this entire thing here will resolve to 2, so it'll be 2 on n pi. Oh yeah, sure, I can resolve how I get L equal to n on 2. Let's go back here in our slides in particular. I'll show you guys how I got that. So, here is such that, go back up here. When we're doing our approximation here, in particular, for our Fourier series with period 2L, the reason why we say 2L here is because, for a fixed period of f of x, the period here is going to be t. But in doing our evaluation here, we say 2 of L. So 2 of L here would be basically equal to t. So f of x here basically has a period of t. And what we're just basically saying here is that t equal to 2L. So L of such, L here will just be t divided by 2. And that's how we end up getting L equal to t on 2. Because we're just basically saying the period, instead of it being capital T here, it's now going to be a period of 2L. So we just say t is equal to 2L, and we just manipulate it such that we get L as the subject of the formula. Alright. So yeah, we're basically at the end of today's lecture, because today's lecture is very short, and I didn't really have anything carded in particular for any example problems or such and so forth. Because at this point, I know you guys will be like watching assignment loaded and so forth from all the other courses, so I figured I should just give you guys a little bit of a break in particular for today. What I can discuss for you guys in particular would be your midterm, which is supposed to be approaching very soon. There isn't a set date for it as yet, but basically I think in the course outline we said it means somewhere either on the 26th or 27th of next week, or on the 2nd or 3rd of November. But once I get a fixed date, I will let you guys know. It's not, I can tell you up front, it's not going to be next week, maybe the week after, but I'll post it up on my LinkedIn to let you guys know exactly when do we have the midterm. As for what you can expect for your midterm in particular, is that so your midterm would be up to, and I'm checking the lectures here too before I don't want to tell you guys the wrong thing. So I'll tell you exactly what your midterm is going to be up to for which lecture. Your midterm will be covering the material from lectures 1 to lecture 14. So up to the end of lecture 14, which is going to be the topic of block diagram simplification, that's going to be the topics that would be most likely covered within the midterm. There will be 3 questions on your midterm, and your midterm is going to be 20% of your final mark. As for the weightings of those 3 questions, the first question will be weighted the least, the second and third questions will be weighted equally. So I believe the weighting shall go 4 marks for 4% for the first question, and then for the other 2 questions it'll be 8% and for each one of those. So that'll be 4 plus 8 will give us 20% in particular. Because how the midterm this year is going to be structured online, basically on the day of the midterm, the midterm paper will release online on My Learning. And I know there's still some people who don't have access to My Learning, so once it releases on My Learning, it would be very helpful if you can get the midterm paper from any one of your classmates, or you can email me up front and let me know you don't have access to My Learning, so I can make some sort of arrangement to send it to you via email, so that way you can actually attempt it. As for the time range, we're still experimenting with the time range. Typically, if you were sitting down in the physical classroom, you've been doing this within 90 minutes. But because we understand that there's going to be unpredictable factors like if electricity go, or if your internet cuts out and so forth, we're going to be having an extended time factor to accommodate for such unpredictable conditions for your midterm. And as of such, you may have like something close to like a 6 to 12 hour time frame for the midterm, but I'm still working on that to see what is going to be the actual time frame. Once I do have a solidified time frame, I will notify you guys on My Learning accordingly with all the relevant information as of such, and so that way you guys will know in particular what to look out for. But what I can tell you is that the material for the midterm will be up to the end of lecture 14. You're going to have 3 questions in midterm. The first question will be weighted around 4%. The second question will be weighted 8%, and the third question will be weighted 8%. So that will give us a total of 20%, which is going to be 20% of your final mark for the entire course. And because we're not doing this in class, this is going to be online. Obviously, it's going to be an open book exam, but your time for actually doing it, like I said, because we're factoring in unpredictable conditions, you're going to have an extended time period to actually submit your work and of such. You will also get instructions as to how to do your midterm. I can tell you in general, it's that we will post up the midterm paper online on My Learning. For anyone who doesn't have access on My Learning, let me know upfront, email me, and I can make arrangements to send midterm paper to you via email. For those who do have access to My Learning, a submission area will be created such that you'll be attempting the midterm on paper, and you basically you'll be writing on one side of the paper, you take photographs of your work, and you just compile it into the PDF, and you just submit the PDF via the My Learning submission portal. For people who don't have access to My Learning, and because I'm making the arrangement to send to you via email, you can also send me the PDF via email as your attempt for the midterm as well. But once all these details are basically going to be finalized in particular, I will post it up on My Learning and let you guys know what exactly to look out for in particular. So yeah, I know you guys basically have a good bit of stuff to do, or you may have some arrangements to take care of and so forth, so that's why today's lecture is going to be somewhat short in particular. The questions in particular would be somewhat like the tutorial questions, yes? But I will tell you in next week's session, even though I did card it for the problem set, I will shift that problem set date accordingly to later on. And next week's tutorial session, we're focusing on particular types of questions that you may expect in your midterm and what sort of questions they will be. I can tell you that for the first and second questions, you have encountered these types of questions in the lectures and possibly the problem sets as of such. The third question will be a question that you will have to think a little bit as to how you can actually apply your skills that you've learned so far into obtaining the answer. But I can also tell you up front that marks will not be awarded on the final answer. Well, okay, how to put this? The minimum amount of marks will be awarded for just showing me the final answer. The majority of the marks will be awarded towards showing me the process as to how you went about solving the problem and how you approached it to get to the final answer. So even though if you end up with the wrong final answer because you took the right approach, you will still get the majority of the marks overall for your midterm. So make sure that you do show all your steps and all your relevant working in order to get your marks, because if you do make an error and you don't show these steps and working, I can't award the marks for you accordingly. Alright, so once I finalize all these details for the midterm and whatnot, and I most likely will finalize it before the end of this week, I will post it up on my learning and let you guys know what to expect as to what day the midterm will be, your time limits, what to expect, how you're going to be submitted and so forth, and all those details are pretty much fine. I am pretty much fine if you write the answers digitally in an app like OneNote and just make a PDF out of that. That is perfectly fine with me. So you're saving paper, save the trees and whatnot, because basically I have a graphics tablet and that's what I've been using for my whiteboard, and it has been pretty advantageous for actually doing most of my work. So yes, I'm perfectly fine if you write the answers digitally in an app like OneNote or Microsoft Word or something like that, and then you made a PDF out of that. That's perfectly fine with me. So long as everything is legible for me to actually understand your handwriting. That's going to be the most critical aspect. Just make sure I can actually understand your handwriting when you submit your stuff. Alright, so are there any further questions with respect to the Fourier Series lecture or respect to the midterm material in particular? You can type out the literal English parts, but I do expect you guys to like possibly draw stuff, or that you'll have to write out equations out of such. But yeah, once it's legible and it's not going to be scrambled all over the place, I'm perfectly fine with that. So you can like just type out whatever the words are, and then when you have to actually do the equations, you can do those digitally using your stylus or pen or whatever you have for actually writing on the screen. Same thing with diagrams, you can draw the diagrams using the pen or stylus. I am not too sure about the plagiarism form part, but I believe that normally you would have to, but I think there would be a statement upon obtaining the midterm paper or in the instructions for the midterm saying that you agree to the university's plagiarism statement as of such and so forth, so that way you guys won't have to sign this in particular. But I'll see what the regulations say in particular with respect to this. Alright, any further questions? Alright, it doesn't seem like we have any further questions, but if there are any further questions, you can leave it in the comments down below for the video, or you feel free to email me accordingly with respect to any questions as of such. Like I said, once I work out the finalized details on the midterm, I will post it up on my learning, so just look out on my learning when I do make a forum post in the course page in particular. And for people who don't have my learning, make sure that you guys notify them about the forum posts and the contents of it in particular, as of such. And also for people who don't have access to my learning, email me up front so that way I know that I need to send you the submission via email. Sorry, the midterm paper via email, and accept your submissions via email. For people who do have access to my learning, you will be able to access the midterm paper online, and there will be a submission area on my learning for you to submit your attempt online as well. The submission area will only accept PDF files, and I will also give a little bit of instructions how to keep the PDF file size small, because we're no longer allowed to put like massive attachments on my learning because of physical space requirements and a whole set of other issues and so forth. All right, so next week lectures are going to be basically on the Fourier transform, and the Fourier transform will be focusing on aperiodic signals, basically signals that are not periodic in nature. And next week Tuesday, instead of doing the problem set, I will basically do a review session for you guys to have an idea of what sort of questions you'll be looking forward to in the midterm, and what you can be expected of for doing certain things in the midterm as of such. Alright, so until next week, take care, be safe, and I'll see you guys soon. Later.